Okay. I think we can begin. Hello, everyone. Thank you for coming today. Before I introduce Jacob Pierce, as always, we reimburse everyone up to $11. If you would like, if you would like to order food and have that reimbursed, I will put the link to submit your receipts in the chat momentarily. But for now, we're lucky to have Jacob Pierce today. Jacob is a current physics PhD candidate at UCLA. He graduated from the University of Chicago Phi Beta Kappa with a BS in Applied Mathematics and a BA in Physics. While at the University of Chicago, Jacob not only was the president of the Society of Physics Students, my predecessor, but he was involved in various areas of research. While researching at Oregon, Jacob created a Python library for combined data acquisition and real-time analysis of the Canadian Penning Trap Mass Spectrometer, which is one of the main components of the ATLAS experiment at Oregon. On campus, Jacob did research in plasma physics at UChicago for Professor Caprioli, where he ran 3D particle and cell simulations of relativistic active galactic nucleus jets to determine particle acceleration mechanisms. Due to his various academic achievements, Jacob was awarded the John Haisler Lewis Prize by the Physics Department and the David Granger Senior Scholarship by the college. Now at UCLA, Jacob develops, runs, and analyzes particle and cell plasma simulations to study the physics of plasma acceleration. And today he's going to talk about the mathematical and computational methods to model plasmas, as well as the physics of plasma acceleration. And now, please give a warm welcome with your virtual applause to Jacob Pierce. Thank you.
Thanks so much for the introduction, Miles. That was the first time I've ever had a introduction, so moving up in the world. Yeah, as Miles said, I was previously the president of SPS, so it's great to be back here and to see that UChicago students are still interested in learning about physics outside what they see normally in classes. So yeah, anyway, moving on to the talk. So today I'm going to talk about plasma physics, which I think is extremely interesting, and hopefully I can convince you of that. So yeah, I'll focus on plasma acceleration, which we'll get to later, but let's get right into it. So here's the outline. First, like I said, I'm going to talk about why I think plasma physics is interesting. And for this section, I'm basically just going to run through a list of many of the things that plasma physics is used for, both in in modern technology, but also in applications to astrophysics and fundamental physics. And after that, I'll explain how you actually do theoretical plasma research, both theoretical and computational. And finally, I'll talk about plasma acceleration, which is what I specialize in. So each of these topics, an entire talk or multiple could be dedicated to, so I'm really not doing any of them justice, but I'm just going to run through these just to give you a sense of how useful plasma physics is. So the first thing, this is how I actually got interested in plasma physics originally, is controlled nuclear fusion. So as we all know, the reason why we have energy on Earth is because energy is produced in the sun. And the way that happens is nuclei fuse to form heavier nuclei, and you release energy in that process for when the input nuclei are light. And so the idea is, that's such an efficient process in the sun. Can we do that on Earth? And so that's what the goal of controlled nuclear fusion is and has been for the last few decades. So this on the right, this is what a tokamak looks like. This is a typical fusion reactor. And it's actually a very bright future for fusion right now because the world's largest tokamak, like I said, a fusion reactor is being built right now, and that's supposed to be up and running in the next decade. So stay tuned for that. That's called ITER. So astrophysics, it practically goes without saying since almost all of space is composed of plasmas, but here are just a few things that plasmas play an essential role in. So relativistic jets, both structure and evolution, cosmic rays. The acceleration of cosmic rays in the first place can only be sustained by plasmas, and cosmic rays themselves are very important in galactic evolution and overall the structure of the universe. Stellar structure, magnetic field generation, the list goes on. And then these images here, this is a jet, and this is a picture of a shock. So this is a process that you can have in a plasma, and this is responsible for, believed to be responsible for many of the accelerated particles that we observe, for example, in cosmic rays. And by the way, feel free to interrupt. I'm being a bit ambitious with how much I want to get through, but definitely feel free to interrupt. So moving on, space physics. This is another area kind of astrophysics, but it's usually kind of categorized separately. So this is the study of plasma processes confined to the solar system. So for example, this is the surface of the sun. This is a flare, and these can only be explained through plasma physics. There's no other way to explain what's going on here. This is a picture of the sun, the solar wind impinging on the Earth. And you can see here, there's this little kind of, this is called a shock. There's this little kind of shield you can imagine. That's actually induced by the magnetic field of the Earth. And that's actually what protects us from the solar wind. So, you know, here we have a ton of plasma physics at play, which is actually one of the reasons why we can exist here. It's because this solar wind is shielded. Okay, so plasma acceleration, this, like I said, this is what I specialize in and what I think is really interesting. So the idea with plasma acceleration, which I'll talk about later, is that by using a plasma, you can generate an accelerating gradient. So in other words, you can accelerate particles in a much shorter distance than you could with a traditional RF accelerator. So the reason why that's such a big deal is because with RF accelerators, you know, they're massive. If you look at a place like the LHC, the accelerator is on, you know, mile scales in radius. And as a result, they're also extremely expensive, you know, because of the magnets and the amount of space that you need and all the equipment you need and all that. So here are just some typical numbers. You know, at LBNL, this is Lawrence Berkeley National Lab, there's a classic experiment where they got 1 GeV electrons in 3.3 centimeters. So yeah, it's kind of crazy. You can get really crazy accelerating gradients. And of course, this if plasma acceleration becomes, you know, a common technology, then that's going to impact every industry which relies on particle accelerators, of which there are many. So here's just a few examples. And this percentage is the fraction of accelerators that are used in that category. So for example, radiation therapy, accelerators are critical for that. You need to have, you know, very monochromatic beams and, you know, very low emittance, very focused beams if you want to do radiation therapy in a localized manner. You know, here are a few others, which I won't go into. And yeah, just pretend you didn't see that. Here's another recent development, X-ray free electron lasers. So the way a traditional free electron laser works is you send particles, a charged particle beam through a series of magnets like this. So this red is the particle path. And when the particles go through, they produce synchrotron radiation going forward. And then you put mirrors like this on either side. So there's another mirror here. And by doing that, you get you can form a standing wave, and that's how a free electron laser works. So the problem with when you try to do this for X-rays, for example, higher frequencies, is that you can't reflect an X-ray with a mirror. You know, you can only do that for lower frequency light. So the idea with an X-ray FEL is you can actually use a plasma itself, like you use the beam itself as the lasing medium, and you can actually produce basically an X-ray laser, which is, you know, kind of crazy, but that's something that we can do with plasmas. And then here's kind of just a catch-all for many things that you can do with plasmas. I'm not going to go into these, but these are very advanced optical techniques that you can use plasmas for. And then, yeah, just a note about, if anyone's interested in applying to graduate school for plasma physics, these are some kind of notes about what these experiments are like that I mentioned earlier. So nonlinear optics and plasma acceleration, those experiments can occur over a range of scales. You know, you can, in principle, go to a lab that has plasma acceleration happening. You know, it would look like a typical AMO lab. You know, you've got high power lasers and, you know, an optic setup, all that kind of stuff. Fusion experiments, I kind of think of as being like accelerator facilities in that, you know, you have a lot of components. No one really understands the whole system. It's composed of many subsystems, which different people are experts in. And so if you worked at an accelerator facility and you liked it, then you would probably like working on fusion devices. Okay, so with that out of the way, I'm now going to move on to how we actually describe plasmas, both at a theoretical and computational level. And yeah, before I even get into that, I just want to say, one of the things that I really love about plasma physics is that it basically combines everything that you know about physics, and you experience all these things. So for example, electrodynamics, that goes without saying, because plasmas are, you know, charged particles and they respond to electric fields. but also fluid mechanics. You can't think of plasmas. I mean, under certain circumstances, you can think of plasmas as just single charged particles, but most of the time you have to consider the collective effects, and that's what fluid mechanics studies. Statistical mechanics as well, that's at like a higher level. And even quantum mechanics, for super intense laser fields, you can actually get to the point where the electric field gradient is large enough that you can actually get to the point where relativistic effects occur, like QED effects. So yeah, this is actually a big topic in Europe right now. They're building some machines that are supposed to access this domain in the next decade, and right now people are doing simulations of this. As far as math goes, if you like PDEs, you will definitely like plasma physics. And the other thing I really like about plasma physics is that the problems themselves are very well defined. It's like the problems themselves are pretty much all PDEs, partial differential equations, and they're just impossible to solve. And then the challenge is to say what you can about them, but it's still a well-defined problem. Like I always felt that when I was experimenting with high energy physics, I felt like some of the problems were just like not very well defined. But I guess that's subjective. And then finally, on the numerical side, there's also all this kind of stuff, machine learning, that's becoming big right now. High performance computing, I'll get to that later, but these simulations we run are very expensive, and they typically deal with petabytes of data. So if you're good with computers and you're good with data, then you would also probably enjoy doing this type of work. So now how we actually describe plasmas. So this is kind of a hierarchy of different descriptions. So from top to bottom is like the highest resolution to the lowest resolution. And so if we start here, you can imagine, in principle, we can write down, if you ignore quantum effects, you could write down the exact equations for what all the particles in a plasma would do. You imagine there's a macroscopic number of particles, and then you write down Newton's laws for each particle. So in principle, that's possible, and that's what n-body simulations do. And this is the associated equation. Typically, I think this is done in astrophysics in some circumstances, but that's typically not done in plasma physics just because it's so expensive. Typically, we work at these lower levels. So kinetic, this is where you're concerned with the distribution function of the particles. So you study the probability distribution of particles in phase space, so both in position space and momentum space. And that's what, for example, the Vlasov equation gives you an evolution equation for that quantity. And the simulation techniques we're used for that are called particle and cell, PIC, which I'm going to talk about in a bit. And this is Fokker-Planck. Some people use that, but this is PIC is the main one. And then below that, we have N fluid. So this is where you kind of remove the velocity dependence of the distribution function, and you're only looking at fluid quantities. So for example, charge density, current density, things like that. In a kinetic simulation, you have individual particles. So there's no, you interpolate charge density for certain steps of the process, but you're not evolving the charge density according to a differential equation. You're actually evolving kind of like charge density chunks. Whereas in the fluid approximation, you're using fluid mechanics plus Maxwell's equations, and you're concerned with things like density, and there's how that evolves according to some differential equation. And then finally, magnetohydrodynamics, or MHD. This is kind of the lowest level, which is still used, but it's questionable when you go that low in the hierarchy how accurate it actually is. But yeah, people still use that, and it's successful under certain circumstances. And I should mention this kinetic. This is probing kind of time and space scales that are associated with like single particle motion. So for example, you could resolve the gyro radius of an oscillating particle in a kinetic simulation. But in MHD, you're typically, for example, or the fluid equations, you're looking at behavior that's far beyond that scale. So yeah, something to be aware of. So these are the kinetic equations, the Vlasov equation in particular. So this whole thing would be called the Vlasov-Maxwell system. So if you focus on this, these are Maxwell's equations. This is as we know and love them. So when you describe a plasma, that's always part of it. So then the other part that we have is how the plasma itself evolves. And if you concentrate on this equation, this is the same equation but for ions. This E is for electrons. This F is the distribution function I was telling you about. So this tells you how this distribution function is a function of t, the time, the position, and space. And at a fixed time, it's a probability distribution for where all the particles are in position and momentum. Okay. So for example, if you if you picked like a small volume at some point x naught v naught, then the number of particles in that box should be F at that point times the volume of the box, approximately. So the way this thing evolves depends on the electric and magnetic fields. So this is how the magnetic, those fields are coupled to the evolution of the distribution function. Now, if you look at the fields, those are coupled to the plasma through J and rho, right? Through the current and charge density. But then J and rho come from the plasma themselves. If you look at these bottom equations, if I told you what the probability distribution function was for where the particles were, you can reconstruct the charge density like this, and same for the current density. And this is the relativistic version. So you can see you have differential equations here, but then you have, these are actually integrals, but they occur in the actual differential equation. So this whole system is a nonlinear, it's not even a partial differential equation system. It's a nonlinear integral differential equation system. So generally speaking, these things are impossible to solve. And that's why this system can only be solved under very particular circumstances, which are for only the most simple systems. So typically, you can use this to some extent for theoretical modeling, but typically these equations are simulated. And this is what a particle and cell simulation should give you an accurate representation of the evolution of each of these quantities. On the other hand, fluid equations, this is what this system looks like. So you still have Maxwell's equations, but now you don't have an integral in these equations. Rather, you have just regular differential equations, which resemble, for example, the Navier-Stokes equations for the evolution of the fluid. So this is, for example, evolution of the charge or the number density, evolution of the velocity field, and so on. So it's kind of, you can think of it as like Navier-Stokes plus coupling to electric and magnetic fields. And this is typically, like I said before, the kinetic equations have a much higher resolution, but this is typically the starting point for any analysis of plasmas, just because the kinetic equations are practically intractable. So, so to move on, so how do we actually simulate these things? The first step is to understand how to discretize a PDE. So, if I go back to the previous slide, we have these equations, we have the derivative in many of these terms. So how do you simulate that on a computer? Well, the simplest way would be to use a finite difference method. So there are other ways you could do this, but this is the simplest. If you consider, for example, the heat equation, this is a PDE, this is the boundary condition, and this is the initial condition. How could you solve this on a computer, given the initial condition? Well, you can use what's called finite difference operators. So you approximate derivatives as kind of a small change you approximate the derivative by linearization. And so this J would be the indexing the position, and N would be indexing time in this case. So to get to the next time, there's only one N plus 1 here, and the rest of these have N. So if you know all the data at time N, you can go to time N plus 1. So that's how you discretize a PDE in general. And that's basically how you solve all these equations. I'll mention the actual coefficients that you choose, these aren't unique. You could discretize this PDE, for example, in different ways. And those the solutions then, the numerical solutions will have different properties. So that's a very important area of study. So the particle and cell method is, like I said, this is the way that we simulate kinetic plasmas. And the way it works is you discretize the PDEs that you can. So for example, these PDEs can all be discretized because they're purely differential. And so you discretize those, but then instead of discretizing the distribution function, because it's an integral differential equation, instead what you do is you use kind of particles. So this is like a picture of what you have. You have a kind of a grid, and then you use these fake particles. Each particle would represent many individual particles, many individual electrons, for example. And what you do is you get the electric fields using the finite difference method, then you use those electric and magnetic fields to push all the particles, so to move them forward a small time step. And then at the new position, you then compute the current density, which is how much they moved, and in the charge density, and then you can plug that back in and repeat. So this is the basic idea. There are many other complications that can be added here, like I said, the way that you choose these coefficients, the way that you actually push the particles makes a difference. But this is the basic idea. By the way, if anyone has questions, again, feel free to interrupt at any time. Whoops. So this is an example. Particle and solid simulations, I should mention, are extremely expensive. So because of this, because you're tracking individual particles, they're way more expensive than fluid equations to simulate. So this is to give you an idea of the type of research that can be done. A very active area of interest is developing reduced PIC models. So still giving you the kinetic resolution of PIC simulations, and still using a particle-based approach, but with a lower computational cost. So here's an example of kind of a brilliant scheme. This is called the quasi-3D algorithm, and this is in the code that our group uses called Osiris. So the way this works is instead of this F could be E, for example. This is some quantity that is part of the finite difference method. Instead of tracking all three 3D coordinates in cylindrical coordinates, what you can do is expand this in terms of the azimuthal harmonics. So you only track, so you can basically reconstruct this thing on a 2D grid of R and Z and track each component separately. And if you do this, what you find is that you can actually write down a different differential equation for the evolution of each component separately. So when you do that, what you get is that you can actually reduce this grid to a kind of hybrid 3D grid, and you need many fewer particles to simulate cylindrical phenomena with high fidelity. So an example of that would be laser wave field acceleration. That's why this was, which I'll get to later, this is why this was developed. You can still get very accurate results with speedups of 100 to 1,000, depending on the mesh size. Another example of how you can make these simulations faster is, this is something I'm working on. So the idea, I'll get to this later again, this is laser wave field acceleration. The way this works is you send in a laser pulse into a plasma, and because of the fact that the wavelength of the laser is far less than the length of the plasma, you can actually do this scheme where you analyze this problem in a co-moving frame that's going to the right. And when you do that, the laser is going to be Doppler redshifted, and the plasma is going to be Lorentz contracted. So in other words, you can decrease the resolution while still resolving the light, and you can actually run the simulation for a shorter amount of time and still achieve the full simulation. So this is kind of a brilliant scheme, and the only problem with it is that in a PIC simulation, when you have a plasma drifting like this, like relativistically drifting, you get this crazy instability, which is not physical. It only happens in simulations, but that's the main challenge with this approach. And so that's modern research on this area is dedicated to kind of combating that. So, but anyway, more details about this. So main line would be this. Based on the argument I just gave you, the speed up is proportional to gamma squared, which is kind of crazy if you do this. And this can also be combined with, for example, that other method I showed earlier, the quasi-3D method. So here's something I'm working on. This is an example of this instability I was talking about. So the instability is called the numerical Cherenkov instability, and this is what it looks like. So in these simulations, each column is one simulation, and we just have a plasma drifting relativistically to the left with gamma equals 20. So this is the electric field, and then this is the Fourier transform of that, which tells you what kind of plasma modes are present. So if I run this, you can see that in this simulation, the electric field rises. So it starts out at 0. I don't have the plot, but it starts off at basically 0. And you can see it rises to basically 100. Whoops. In a short period of time. So to give you some perspective, these are normalized units. This would mean that the electric field magnitude times the electric charge would be 100 times mc squared of the electron. So this makes literally no sense. And that's what you get if you just try to use a regular, like the same finite difference operator I showed earlier, the simplest one you could write, and use that to evolve the electric field. So I'm not going to go into detail on the rest of these, but basically, if you change the field solver and then use the right current filtering scheme, so like you apply basically a low pass filter in the right spot, you can actually eliminate this instability more or less, which is basically the key to doing these boosted frame simulations. And then finally, I'll skip this. This is an example of a boosted frame simulation that I recently ran. So the top is laser wave field acceleration, which I'll get to later. And then the bottom is the same simulation, but run the booster frame with a speed up of 100. So yeah, this has been a very interesting topic, and I think there's a lot of potential for this in the future. So then finally, I've been talking about plasma acceleration this whole time, which is what this movie is an example of. So now I'll tell you more about this, because I think this is, in my opinion, the most fascinating thing you can do with plasma physics. So the idea started in the late 70s with these two professors, Tajima and Dawson, I think they were both at UCSD at that time. And the basic setup is you imagine that there's kind of a force going through the plasma, which is propagating like this at a constant velocity. And the force is a delta function, which always gives a kick in the longitudinal direction. So clearly this is idealized, and we'll get to how you could actually do that in a minute. But that's the setup. You just imagine that that's the case and that this force is propagating through a plasma. Now, if you plug that into the fluid equations that I showed you earlier, and you use this, another property inherent to plasmas that I haven't talked about, but one would talk about in explaining this in more detail, you actually get that you get a kind of wake structure, kind of like how a boat forms a wake when it goes through water. In this case, this is where the force is at this given point in time, and it's moving to the right. And trailing it, the solid line is the electron density, and the dashed line is the electric field. So you get a kind of sinusoidal perturbation for both of these quantities. And the reason why that's so important is because, for example, the electric field is both of these quantities are propagating to the right along with the driver. So you can imagine the electric field is, for example, positive here. If a particle was going at the same velocity at VF, and it ended up at this position, it could basically just ride this wave and keep getting accelerated because it's going to remain in a similar position but keep experiencing that positive electric field. And so that's the idea with plasma acceleration. And there are many. So I'll go into how you actually do this. So the simplest way is called plasma wake field acceleration. So in this scheme, you use as the driver. That's what this F is known as the driver. You can send in a pre-accelerated particle beam. So in other words, you send in a beam into a plasma, and then the beam itself has kind of like a electric field associated with it, which pushes away the particles. And so that's the kind of kick that you get. And when you do this, you actually you do reproduce these wakes for kind of low density beams, but for very high density beams, you start getting very relativistic and nonlinear wakes, and they look more complicated than this. So this photo is from Wikipedia. I'm not sure, the actual simulation. I'm not sure if this is an actual simulation or kind of just a model, but this is generally what the picture looks like. You have the beam here, and then you get kind of a bubble like this, and it's not plotted here, but the electric field would be going like this, and then particles at the back of the wake who get stuck in this this electric field and keep getting accelerated. Ultimately, they'll then escape and pass the driving beam itself. So that's not what I work on, but there are problems with this, but this is an active area of development. And this could arguably be said to be the most successful way of doing plasma acceleration so far. The other main way that people are working on is laser wake field acceleration. So this is what I focus on. So with laser wake field acceleration, instead of sending in a particle beam, you send in a high power laser pulse as the driver. And the reason why this works is because of this thing called the ponderer motive force. So if this is the envelope of the laser, and so the actual laser would be this times a rapidly oscillating, like a cosine, of omega t, there's this thing called the ponderomotive force, which tells you that the effective force felt by a single particle at the edge, will be away from the high field region. So for example, particles here would get a kick that way, and then particles here would get a kick that way. So the reason that's a way that you could achieve this idealized driver, because you need to have like a kick in the x direction, moving kind of at a constant velocity. Now, in practice, this is an extremely complicated problem because the laser pulse itself evolves. It doesn't just move at a constant velocity. Another issue is that the laser pulse doesn't just move at the speed of light. It actually moves slightly slower because a plasma is a dielectric. So that is an issue I'm going to talk about more in a bit. But then you can also see you get extremely complicated effects following the laser. These can really only be studied using big simulations. And you can kind of capture elements of the theory through scaling laws if you run enough big simulations, but it's very hard to analytically derive results without running simulations. So here's more info about laser wave field acceleration, this concept I just showed. So the way that the pulse evolves is extremely important because the pulse itself is what's giving the kick. So if the pulse gets deformed, for example, then you may no longer have a high quality electron beam produced. Another issue is pump depletion. So this is the laser itself has to it loses energy in the process of forming this wake. And so the laser that's another aspect of evolution of the pulse. It needs to keep propagating and not, lose its energy too quickly. Another important issue is dephasing. So as I mentioned, the pulse itself goes slower than the speed of light. That means that at some point, particles if they keep getting accelerated, can pass the pulse. And so that's no good because you need the particles to remain in the wake so that they can keep getting accelerated. So this right now with conventional laser wake field acceleration schemes, that places the fundamental limitation on how much energy you can actually get out of electrons because they eventually outrun the wake, the pulse. Another issue, this is actually an issue for both laser wake field and plasma wake field acceleration, is that the particles have to end up in the wake in the first place. So how does that happen? Well, with laser wake field acceleration, you can get self-trapping, which is where if the pulse is chosen appropriately, you can get some electrons, for example, to populate that part of the wake. But it's not a trivial issue. Other things that you can do are use external injection, which is where you time the pulse, the laser pulse here, and then a particle beam right behind it at the right spot so that when the wake forms, the beam that you injected is in the wake, and then it'll get reaccelerated. And then there are these other crazy schemes. Like another one is called ionization injection, which is where you send in two pulses. So here's the first pulse and here's the second pulse. And the first pulse is just a regular driver, but the second pulse is timed so that it ionizes the medium at the exact spot in the wake where the particles have to be. So like the first laser is lower intensity, and then that forms the wake, and then the second laser ionizes particles so that they end up in the wake. So there are all these kind of ingenious schemes to do this, and it's very much still an active area of development. And then, so another issue is that when the particles are actually in the wake, they start evolving, and they change the structure of the wake. So this is also an extremely non-trivial problem. And, again, this can really only be studied using Higgs simulations. So here's more about this dephasing issue I talked about earlier. So this is the issue where particles can outrun the driver. So the current way around this for when people talk about how they're going to use laser wave field acceleration to achieve, for example, TeV electrons, GeV can be done with just one laser pulse. But the question is, how do we get TeV using that technology? And so the current kind of proposed method for doing that is to stage these accelerators. So use one laser to get a 1 GeV beam, and then use the external injection method to then use this method again. So inject that into the wake of another laser wave field accelerator and keep repeating that process. Now, the problem with that is that's extremely difficult to do. I'm not an experimentalist, but I know this is an extremely hard thing to do because first of all, the beam has to be the exact orientation of the beam compared to the laser pulse. It can't be slightly off, it has to be exact. That's very difficult. And then the other issue is the timing has to be perfect, to get in the right spot of the wake. So this is an extremely difficult issue to solve. So here's something that I'm working on. This is kind of a proposed way around this. So this is called the flying focus technique. And the way this works is you use a very special pulse, which has the property that it kind of avoids, the pulse just kind of keeps propagating. It doesn't, you can make the pulse propagate essentially at the speed of light and control the velocity of that pulse, even though, normally a pulse should propagate at the group velocity of the medium in a plasma. So the way this works, this is called the longitudinal chromatism-based flying focus. The way this works for this case is you send in a pulse, which is chirped. So the blue light is kind of at the front, you could say. Like there's more rapid oscillation at the front of the pulse than at the rear. And then you send this thing through a diffractive lens. And this lens has the property that it focuses different colors to different points. So if you just sent in a monochromatic beam, the red light would get focused here, and the blue light would get focused over here. So now if you send in a pulse, which has this chirp, then because you're controlling the timing of when each color hits the lens, you're also going to control the timing of when each color comes into focus. So in other words, by controlling the timing in the pulse, you can control what the actual envelope of this thing looks like. And so you can actually get crazy pulses. You can get pulses that go backwards effectively. You can get like oscillating pulses if you put a sinusoidal chirp on this thing, which are all very interesting. The main application to laser wave field acceleration here would be if you can get a pulse to go at exactly the speed of light instead of at slightly less than the speed of light, then you could solve this dephasing issue. And that's something that we're working on now. And then here's another way that you can do this. This is a spherical aberration based method. So instead of focusing different colors to different points, in this case, if you look at this optic focuses different rings to different points. So for example, the outermost ring gets focused to here, and the innermost ring, so this one, gets the focus to all the way out there. So now if you control the timing of these rings, then you can control in the same way the kind of focal velocity that you get. So for example, in this case, you start here, you can add a delay to each of these rings using this is basically just a mirror with kind of a different depth at each radius. And so you can add a delay to each ring, and by doing that, you can get the different rings to arrive at different times. And in doing that, you can similarly get a pulse that either goes back and forth or goes backwards, or the case that we're interested in, which is go exactly at the speed of light and solve this dephasing issue. So this, as I say, this is fresh off the press. This is from a simulation that I ran recently where I kind of have this the chromatic flying focus where you have different colors focused to different points. And if you focus closely on this region, like 0 to 20, you can see the pulse kind of goes backwards in that region. So this is kind of just proof of principle showing that this thing works. But that's the idea. You could get this pulse to go. I think this is actually a superluminal, or no, this is -1. But you could also do this with a superluminal velocity if you wanted, which is kind of funny. But yeah, that's all I had. So if anyone has questions, feel free to ask.
Thank you very much, Jacob. Yeah, feel free to raise your hand if you have any questions. I actually had a question. Could you go back to that first slide you had where you had the relativistic, the videos of the plasmas relativistically translating to the right?
What was that? Yeah, this one, right?
Yeah. I was wondering if you could discuss why you're analyzing the Fourier transform of these pulses, because it's not exactly obvious to me.
Yeah. So the first people running these simulations, they just ran the drifting plasma with this so-called Yi solver, which is like the second order finite difference algorithm. And they're like, yeah, this algorithm's great. We're going to send in a pulse, and we're going to use a drifting plasma, and then that's going to give us a simulation that has a speed up. But when they tried to do that, they saw this ridiculous instability. And people were perplexed what they're actually seeing here until they took the Fourier transform of it. And when you look at this, what you can see is that certain modes are getting preferentially excited. So this is basically what the evidence would be, that this is kind of this is not just noise, this is a systematic instability, which is getting excited. And so I didn't mention this earlier, but you can actually derive this curve theoretically using you can't, you have to use like a root finding algorithm, but you can write down, for example, the polynomial whose roots would give you this curve in k-space. And same for these. For example, this is a higher order solver. If you run the same simulation, you have the same problem, the field blows up, but you get a different pattern. So to comment more on this, actually, this is good because there's a huge difference between these, which is that in this case, the growth is limited to high K. So this if you use this solver, you can actually combine that with a filter to eliminate this part of the instability. So if you do that, you can actually, that's what this plot is, but then you get another instability over here when you do this. But then you can use this other modified solver to suppress it. So this is what we're using in these simulations.
I see. Thank you.
Yep.
Any other questions? No, those is asking questions. I have another question. I was hoping if you could discuss a little bit the role machine learning algorithms can play in producing the simulations.
So yeah, I don't even have a slide for that, but so one method that I've recently seen in fluid mechanics, which is there's actually a professor here who's starting to work on this, which this hasn't really been done in plasma physics before, but this is something that's becoming hot in fluid mechanics, which is this idea of data-driven discovery, which is where you know the equations that are being obeyed. You know, for example, in the case of a fluid, you have, actually, this is the right slide. So yeah, in the case of a fluid, you have the Navier-Stokes equations, which are like these, without E and B. And in a simulation, for example, or in an experiment, you know what data you observe, right? For example, in the case of an experiment, you might, in a plasma, for example, you might have an experiment where you have a probe inside the plasma, and you measure, for example, the voltage, which could tell you the electric field at that point, or the density at that point. So in other words, you have like kind of subsets of the data, and you know that data should be evolving according to these equations. So then what you can do is this technique to kind of use a neural network where that data is the input, and you use the fact that the data has to obey these equations to train a kind of neural network that will tell you what the other quantities should be. So for example, if you measure only the density, then you can get other quantities, not only at that point, but in the vicinity of that point. So that's one technique that's becoming really, so for example, another method, another case where this could be applied is if you measure the dye concentration in a fluid, you could use that to reconstruct, with this technique, you can use this to reconstruct actually the entire fluid flow, not just at the dye points.
I see.
Actually, I should mention another area where this is actually being applied in our group, someone else is working on this, is someone's trying to train a network to give you the optimal pulse shape, which is a very sensitive parameter, for example, laser wave field acceleration, for optimizing, for example, the brightness of the beam that you produce. So I guess that's more of a regression than actual machine learning, but it's a similar idea.
Are there any other questions?
I like a question.
Yep.
I think you showed a slide where like you talked about like how these particles are simulated. Like I think like you showed this sort of figure, like you form a mesh and then each mesh is like part. It's like, is like gravitational simulation like astrophysics where like people model like particles and stuff in gravity. So like is it like the same sort of like idea behind it? Like sort of you like like you boil all the physics down to like these grids, and then you like don't resolve the microscopic scales, but like you sort of average over
Yeah.
each grid. Is that sort of like a similar
So
approach?
in yeah. So in particle and cell, you do resolve the microscopics. Like there's no way to run a particle and cell simulation without resolving it. So in astrophysics, typically you would use one of these other methods. You would use NFluid or MHD. So these are the scales where you don't resolve the microscopic details. Now you can still have very complicated behavior. Like you still have turbulence in both of these, for example. But you won't have, for example, phase space instabilities captured in these. For example, in a kinetic simulation, if you have counter streaming particles, where like for example the distribution function is a delta function of particles going this way and then another subset of particles going that way, you'll get an instability and the plasma will basically explode. But you won't ever see that in these types of simulations. Now, of course, the challenge is how can you take the microscopic details of kinetic simulations and use those kind of as input to improve the NFluid and MHD simulations. And I think that's something that people work on. For example, microscopic details can play an important role in transport, like particle transport. And I think people try to account for that in deriving transport coefficients in different fluid models. But in general, that's an extremely challenging thing to do. And of course, I should mention, it's generally impossible to simulate full-scale kinetic simulations just because they're already expensive just to simulate microscopic, regions. For astrophysics, that is, just because the separation of scales of, for example, system sizes to mean free paths is enormous.
I see. Okay.
Does anyone else have any questions? All right, well, thank you very much, Jacob, for your time. And let's please give Jacob another round of virtual applause.
Yeah, thanks for having me, Miles. I hope that I've convinced some of you that plasma physics is interesting, maybe to look into it a little more.